Okay, in this next scenario, what I want to do is I want to take the breast cancer situation and the decision making we talked about there and apply it to statistical decision making. And in your books, it'll be chapter 8 around pages 244 to 248. We're specifically going to look at page 247 right now and talk about that idea of hypothesis testing. If you remember back from the previous unit or the previous lecture, we said when we do hypothesis testing, what we basically do is we set a criteria of 0.05 two-tailed. And if you look in your book here on page 247, figure 8.6, if you look at the value of 1 or plus or minus 1.96, if alpha is 0.05 and it's a z-test, what we basically decide is if we collect data and it's above or below 1.96, we say, well, that result could have happened due to chance, but the probability is less than 5% that it did happen due to chance. So we're going to say it didn't happen due to chance. It happened because of whatever the variable was. Of course, we hope we're right with our decision making there, but the idea is we just set that criteria very much in stone. And we hope that that's the right decision. So that's the hypothesis testing and the criteria. And what I wanted to do is I wanted to give you a real-world example of this and focus specifically in on my asthma situation, because a real-world example I think will make this a lot more clear. So if we take the asthma case, what we hope happens with asthma, and if you remember the first example I went over in the last lecture, we collect data, we get a t-score, really, really high, something like 4 or 5, I think it was even 7 there, which is way out to the right, and we say, well, the probability of getting this due to chance, SPSS tells us, is 1 out of 100. So we say we have statistical significance. So we collect the data, the critical value falls in the rejection region, and we say, oh, this asthma program, it really works, it really helps people. Now, if that decision is right, that is called a hit. And I'm sorry, I can't stop thinking hit, you sunk my battleship, if you ever played that game. But that's a tangent. So that would be called a hit. If in reality my program really does work, and I collect data that says it works, that would be a hit. But let's say I collect the data and it shows statistical significance, and let's say that that was just a statistical artifact, that it did happen due to chance, and my program really is not effective. So if in reality my program doesn't work, but yet I collect data and it says it's way out there in the extreme, if I make the decision that, yeah, my program helped, but it didn't, that would be called a type 1 error. We never know for sure, but that would be a false alarm. But we want to try to minimize that. Let's say then I collect more data from another trial, and let's say it shows that the p-value is like 0.74. which would be non-significant. If I collect that data and I get a low t-score, then I'd say, oh, look, my program doesn't work. Well, if that was a correct decision, then I'd have a correct no decision, but I could also have a situation where I collect data and don't show an effect, and I might have a type 2 error or miss. So statistical decision making is kind of wrapped with kind of these yes, no decisions, and we don't know if those are always right or always not right. We hope they're good, but we try to minimize these type 1 and type 2 errors. So the best way that I can actually explain this to you is going over the example of the appendix that we actually have for some of the asthma results in the face-to-face studies I used to run. And I actually gave that to you as a case situation. If you look at Appendix A, that's actually a table of all the results that I had from the 1998 study, the first study I ever ran, 7 weeks of asthma education. And as you mostly said on the discussion board, we hope the treatment effect is high, because that's the numerator. We hope the standard deviation is small, because that'll contribute to the standard error of the mean. Then we look at the t-score. We want that to be large, and then we want the probability to be less than 0.05. So if you look at Table 1, you would correctly conclude that only for asthma controlling your life and what chest tightness does our program actually work. So we collected some other results there, very interesting as far as restriction in sports, felt dependent on sprays and some other things, it doesn't look like we had very much there. And that was indeed the case. The reason for that, and what I was trying to get to in the discussion board, the reason for this is probably due to an issue called power. Power is the ability to have hits. When you design an experiment, before you run it, you usually do a power analysis to say, how many people do I really need to have in this study to really show significance? You do a power analysis, and then the computer says, well, what do you think your treatment effect is going to be? So you do a power analysis before you do the experiment to see how many people you'll need to actually show significance. 7 people is what I had in the 1998 study. When I first ran that, that was not enough to have sufficient power. But then when I added another 7 people in 1999, if you look at the results there, we had many more results that were statistically significant. And this was probably due to having increased power. So power is a good thing. You would say in the first year I ran this, I probably had a lot of misses. Things like feeling tired. If you look at that one in 1998, feeling tired, the probability was 0.11, was not significant. If you look at it, there was a very large treatment effect for feeling tired. 0.88, that's a pretty large treatment effect, but look at the standard deviation. But then when I ran it for the second time, the standard deviation came down just a bit, but the doubling of the sample size really helped it to become statistically significant. So when you run a study, you want to have sufficient power. Doubling my sample size certainly led to that particular situation. So hopefully that makes sense for you. So you want the idea of power there. Let me see if I can get through these other elements as well. Next idea, statistical versus clinical significance. If we go down to, what is it, Appendix D. The idea is, let's say I run a speed reading course, and let's say it turns out, you ever taken a speed reading course, that before my program people can read 150 words per minute, and after my program's done they read 153. Would you spend $10,000 taking my program? Probably not, because it only helps you with 3 words. But let's say I recruit 10,000 adults into my program. Well, if I put 10,000 adults in it, and if I run a t-test with that, I'd actually get a numerator, a treatment effect of 3, and I'd get a denominator of 1. And so I'd get a statistically significant result. This would be a situation of having statistical significance, but no clinical significance. So this would really not be a good thing. It was just because I had so many people that I was able to show significant results. So with that being said, I think I'll close this lecture at this point in time. Thanks. Bye.